Thank you, Johan, and thanks for organizing this very nice conference. It's good to be back. I remember that last time I was in this place was in 2009, so that tells you about that I'm not a PhD student anymore. So what I want to tell you is this. I think it's unmuted. I want to tell you about these 7 works in some kind of unified framework that we started about 2 years ago, realizing that a good part of what we have been doing for the feed-forward fully connected neural networks actually can be used and transferred to study the attention, the key layer in the transformers. And so all these papers, they are kind of split by 2 types of models. I will explain you how they are different. And what they have all in common is that they all are about attention and high dimension analysis of the generalization properties. So I will be training the keys queries, and values were mostly values in some of the papers. In some others, they are not present for simplification, but understanding that. So to kind of set it a bit more broadly, what I'm aiming at here is Johan introduced yesterday very nicely the need for toy models to kind of allow us to proceed in understanding what's happening today in AI. And when I think about toy models, I kind of like to list or keep in mind these 4 ingredients that a toy model must have to be a good toy model for AI, for machine learning. And these 4 ingredients, I think of them as inseparable. If you dismiss any one of them, it will not be, for me at least, not a good toy model. In a sense, you will be throwing away the baby with the water. So what are the 4 ingredients? The first one, let me start with the one, is the model for the data and the tasks. So this is necessary because if we do not assume anything about the data and the task, we are just in the world of the data and tasks that are the worst case created by adversary, where we know that these problems are computationally hard. So there is no hope to actually prove anything or show anything positive. So we do have to model the data. The second thing is the neural network architecture. What kind of happened in the past 20 years was largely about realizing that certain architectures are good and certain less good. So we kind of want to keep that into account. The third point is the algorithm. One needs to explicitly consider the training. Again, as Johan stressed yesterday, the core mystery in all this is, why is the learning computationally efficient? If we actually dismiss the algorithm, then we are back in just approximation and statistics, and there we understand things, but it's useless if things are approximable and statistically possible if they are not computationally possible. And so for me, the big mystery is characterizing what actually makes the problems on which AI can work computationally feasible. And the 4th ingredient is the large size limit. That's I didn't used to put it in, but in the past, say, 5 years, it became clear that the scaling things up is somehow crucial. The scaling laws drive the industry today, and it is, as we already heard yesterday in several of the talks, it's not, that's part of the modeling, like which large size limit should we take? We have several sizes that could go large at different rates or in different orders of the limits. So that is a key ingredient as well. And when I say solvable models, I mean kind of in the statistical physics sense, like the Ising model in 2 dimensions is solvable in the sense that we can write a closed form equation that comes in terms of what in physics we call order parameters. In statistics, we could call it sufficient statistics, that describes what we are interested in the model. And in neural networks, what we are interested in is to describe the statistical and computational limitations. So something like, what is the generalization error that is achievable computationally efficiently for a given number of samples? So I want an explicit expression for that under some simplifying assumptions that are specified in these 4 ingredients. So that's kind of the roadmap. And in the roadmap, there has been a lot of work in the past. So existing solvable high-dimensional models were mostly about, and I can split it among the 4 ingredients. So on the side of the data, Johan told us yesterday about the Gaussian single or multi-index model that we can also call a teacher-student model. Those are very related. We can make the data not exactly just IID Gaussian. We can put them covariants or spikes or make them mixtures. So all those has been studied. On the side of the neural network, what we understand quite well would be the linear learning method. So linear regression, kernel regression, random features, variants of thereof. And then the two-layer neural networks, so one hidden layer feed-forward neural networks. We have a lot of and good progress on that side. On the side of the algorithm, the kind of key question is the empirical risk minimization with the stochastic gradient descent. But since we model the data, we can also be interested what is statistically the base optimal generalization error we can get for that data set. And for that, algorithmically, we need to sample the posterior, and this approximate message passing algorithm is kind of a key tool to understand when that sampling the posterior is computationally efficiently doable. And the large size limit in the linear models, we only have two sizes mostly, the number of samples and the dimensionality of the data. So the high dimensional kind of linear regression is when we send them both proportionally to infinity. So we have just say 5 times more samples than the dimension, or maybe half the samples than the dimension, but not much more, as kind of in the traditional statistics where maximum likelihood is consistent. In this limit, it is not. So we need to think a bit better. So the dimensionality, the large size, comes with the curse, and we already heard about the curse yesterday again in several talks. But from my point of view, or from high dimensional statistics point of view, it also comes with a blessing, as David Donohoe very nicely coined it. And this blessing of dimensionality, the fact that under suitable assumptions, we can actually describe a probabilistic, very high dimensional system just in terms of few numbers, these order parameters. That's the very essence of statistical physics. The kind of physics that is able to describe the gas in this room or how liquids behave, that's exactly what it is doing. So that's in essence the high dimensional statistics 100 years before it became a thing in statistics. So that's just this historical, like people in physics have been a bit ahead because they thought about these high dimensional problems, where in physics the dimension is the number of molecules. So it's of course very big, 10 to the 23 or something like that. So that's kind of where the physics kicks in. And if I should kind of give the physics vocabulary to my 4 ingredients, we can think of these simplified models as mean field spin glasses, where the mean field, okay, here I really mean it in the sense of the dimensionality of the state space being very high. Yesterday we heard about mean field with a bit different meaning, so it's a bit overcharged, this term. So here it's quite different what I mean by mean field. The weights that are being trained in the neural network, if you are familiar with the Ising model, imagine them as the spins that are moving. And then the data, that's the structured disorder, if you are thinking of a disordered kind of physics systems. The architecture of the neural networks that describes the interaction between the weights and the data, between the spins and the disorder. And the estimator and the algorithm, that's actually the description of what the energy function is and what is the dynamics that is running there. And we are not necessarily thinking of equilibrium when we run the gradient descent. It's highly out of equilibrium process. And the large size limit is the thermodynamic limit. So the study of neural networks with this kind of strategy in mind started already in the 90s, and there are many papers. And these old papers are sometimes tricky to read. So here I gave you the 2 very nice reviews and 2 very nice books that were written back then. So they were not so much about deep learning, but a lot of the kind of core ingredients of how to proceed with the modeling of these systems was actually established there. Okay, so now back to the attention, because so far what I said, all this majority of this work was about the perceptrons, feed-forward neural networks. But who cares about them if everything today is running with transformers? So what do we do to proceed to study transformers? So first we need to, okay, transformer may look to some of us as a big mess. So let's extract from it the key ingredients that are different. And in my point of view, there are really three here that are different from the, crucially different from the multi-layer perceptrons. And the first one is how we actually present the data. In linear regression, each sample is just a d-dimensional vector. But a transformer doesn't see each sample as a d-dimensional vector. It sees it as a sequence of length t, so think of t of the number of words or the time if this was a time series, of so-called tokens that themselves are d-dimensional vectors. So at the input there is a matrix, t times d matrix, whereas in linear regression or in regression with fully connected neural networks, the input is just a vector. So that's one big difference. Why do we present the data as a matrix, right? We could also just flatten them and present them as a vector. Like, would that really be worse? So it looks like yes, because otherwise we would not be doing that. But that alone is an interesting question. Why do we actually tokenize the data rather than flattening everything? So it's the first key difference. The second key difference is how they are trained. So they are not trained in this supervised way, as we usually think of perceptrons or linear regression. They are trained self-supervised by next token prediction usually, or the variants of the diffusion models that Jon also introduced yesterday. And the third key ingredient is that they do include the multi-layer perceptron layers that are applied token-wise. So they are kind of a d-dimensional input perceptrons, and the weights are the same for every token. So those layers exist. But there are other layers. So you see these perceptrons, they don't actually mix the tokens together. They are just applied token-wise, like every word is treated the same. But the words need to interact. So the layer that makes the tokens interact is the attention layer. And again, we saw it yesterday in several of the talks. It has this form. It's an attention matrix that is a t by t matrix. That is the number of words times number of words. It's kind of a similarity matrix, how much each word should pay attention to another word. And this matrix is applied to this in a sense could be one layer of a perceptron, because we just take the data and we multiply them by a matrix, the value matrix that is t times that is d times d matrix, and we do the same for every token. And then the way this attention matrix is constructed is similar. We also take the data, we multiply them by a matrix that is d-dimensional in one of the dimensions, but the other dimension doesn't have to be d. In practice, sometimes people take it the same. R and D would sometimes are the same. In the state-of-the-art models, usually this rank kind of parameter, or this width of these key inquiry matrices, are taken as the dimensionality over the number of heads. That's some like ad hoc rule that everybody seems to be using for no kind of theoretically justified reason, in at least as far as I know. But it has this form that again, each token is multiplied by these matrices key inquiry that were learned, and that together creates a t times t matrix that then reweights how the different tokens are sent to the next layer. Okay, so it's this kind of a mixing the token, like mixing along the embedding dimensions with these matrices, and mixing along the token dimensions with this attention matrix. So that's what it is doing. And then the MLPs are leaving the tokens be and doing everything, always the same thing for each token. All right. So now, if we want to move forward in the space of exactly solvable models, I go back to my ingredients, right? We need to account for those things in the ingredients. So on the data side, I said the key thing is that we are presenting structured sequences of tokens rather than vectors. So the very least that we need to do in order to model attention is to do that, to actually present matrices at the input, not vectors. Okay, doesn't seem so complicated to do. On the side of the algorithm, ideally we would account for this mass token prediction, that the next token is predicted from the previous ones, which is a self-supervised way of training. On the architecture size, we would like to account for this attention layer, to pass, to push the signal through that and see what the training does with that. And when it comes to the large size limits, well, here we have also the number of samples that will be as large so that what is being learned is non-trivial, that neither random guessing nor everything is trivially easy. But we have other sizes, at least two other sizes. Since now we are presenting the data as matrices, we have the width and the we have the two sizes of the matrix. How long are the sequences and what is the embedding dimension? So with that, we already have at least three options how to make things grow large. Either both of them are large, right? The third option, or one of them are large and the other one is small. So we kind of, which of these options is more reasonable? So I think all three are reasonable to explore, and we are in my group we are working on all three of them. But in this talk, I will focus on the first one. All the models that I will be telling you about are models where we have sequences, but they are short. Say they are 5 words or 10 words, not millions. But the embedding dimension is large. So in practice, the embedding dimension is something like 1,000 or the 1,000 thing. And the context length is very long as you are able to do. So here we are a little bit in the, so the third case is closest to practice. But okay, we managed to make progress in this first case where embedding dimension is large and the sequences are short. And I will not be considering the self-supervised learning. That's the next step. I will still be considering supervised learning. So there will be attention layers. I will be considering sequences of tokens, but the output will not be the next token, but some supervised task. And I will show you which ones. Just a cautionary note about what I mean by model. That's again a word that is overcharged. It means many things. So in my talk, it mainly means two things. So either is the model for generating the data, so this ingredient, what actually is the toy data on which I'm working, or the model is often just the ansatz that the neural network represents of parameterized function where the parameters are being trained with the algorithm. So often just the neural network itself is called the model. And what makes it particularly sometimes confusing to distinguish the two in my talk is this following idea that comes from the papers in the 80s, this teacher-student idea. When you ask what is actually a good model for the data, well, there are many options on toy data on which you can analyze something, how you could pick them. And this idea that is very influential in the field is actually to take the inputs completely unstructured, to take a ground truth neural network that we call teacher, again, unstructured in the sense that all the parameters in there are just Gaussian random numbers, and generate the outputs with that. And then you present the inputs and outputs to a student neural network that may have the same architecture or different architecture, both are interesting. And then you ask whether that student neural network can actually learn the same function, the function that the teacher represented. Okay, so often kind of the teacher and student model, they look similar, the model that generates the data and the one that is actually learned to use. But it's important to distinguish them, the one that models the data and the one that is used to learn from the data. Okay. So now we are almost ready to define the two models that I will be talking about. So I will kind of be writing things with all the indices because at the end of the day, maybe that's kind of a physicist deformation. I find it like the clearest. If I have objects, then when I talk of sequences of tokens, right, I will call them X, and then they will have three indices. So mu will be the index for the sample. So each sample will be different mu, and I have n samples. And then I have the indices that are deciding where I am in the token space and where I am in the embedding dimension space. So I will stand for the index of the embedding dimension, and A will stand for the index of which token I am at. So, of course, language, code, proteins, many other things. When you tokenize images, you just take small patches in the image and you say, okay, one patch is a token and the pixels, the size of the patch is then the embedding dimension. Like what is being, all the data are tokenized these days before they are fed to the large language model to train. Okay, so now in this list of papers that I want to present, let me define what I mean by this sequence multi-index model and the attention index model. And then I will tell you a bit about how we are actually solving them, how we are getting these closed form equations. And then I will tell you three kind of snippets of the insights that we were able to extract in the papers that are the most recent ones, this one and this one and this one. All right, so the sequence multi-index model, it really is just the multi-index model where we add a index, additional index that indexes the where we are in the sequence here. So this is very similar to what Johan wrote yesterday. This is the data. There is some ground truth vector on which we project, and then the outputs is some arbitrary ground truth function f star. The stars always in the talk will be for the ground truth, and when there are not stars, that's the model that is learning or the weights that are being adjusted in the learning process. But the stars will be always the teacher weights or the teacher ground truth function. So if we didn't have this little a here that goes from 1 to t, the number of tokens, then it would be exactly the multi-index model. This is the d-dimensional scalar product, and then the b, this index that runs from 1 to p, where p is the number of indices. So we can have, say, 5 index models, this function depending on 5 different projections of the data on 5 different directions. But here we have that, and on top of that, we do it separately for each of the tokens. Okay, so we just need to add that index in the consideration, and that the t is small, so that actually, for those who ever worked with the multi-index model and you have in mind some of the techniques, you see immediately that this will not be such a big trouble actually to add this index there. This is kind of, all the methods will become a bit bulkier, but things will go through. So the sequence multi-index models can be studied using the very same tools as the multi-index models, and as we saw yesterday, the multi-index model is a powerful lens into the learning dynamics and generalization at the same time. And then okay, this looks like so rather simple and so generic that you're asking yourself, where's the attention and how does that actually represent anything interesting? So indeed, on a first sight, it's not like completely obvious, but special cases of that, how we actually set this function f star and what this p is, can model various things. So for instance, in this paper, we modeled phase transitions between learning from positions and from the semantics of the tokens. This paper by Pierre Marion and Claire Boyer and Ludovic and Gérard introduced a very nice model that is called the single location regression that I will tell you a little bit about. Or also deep attention only. So in a similar sense as Andrea was considering yesterday, he removed the multi-layer perceptrons from the deep attention architecture. So in that sense, the same, but what is different here that I will be actually training the key and queries here. So we can represent deep attention only model in this form. And let me kind of show you what I mean by that deep attention only model. That's when I take, as I said, the inputs are just Gaussian IID numbers, matrices, T by D matrices. And all the structure that is being learned is in the function from the inputs to the outputs. And what is the function from the inputs to the outputs that I will be able to study using this tool, this model? It's, for instance, I can take L layers of attention, where this is the Lth layer of attention. L here is the index of the layer, and here I have the skip connection. Here I have the softmax. Most usually this nonlinearity is the softmax, but we can keep it pretty generic. And now here, that's actually the self-attention. The W matrices here, they play the role of the key and query, and here I wrote it in the form where the key and query matrices are the same. So that just simplifies my life a little bit because I have twice less equations at the end, but it's not like a principled obstacle. I can untie them and I will just have twice as many equations. So we haven't gone through that in detail yet because it's just technically heavier. But these W's play the role of the keys and queries. And these are the ones that the teacher is using to generate the data. And then there will be the ones that will be trained to learn on that data. And so you see, it doesn't look very similar to the previous expression, but when you actually work with this expression, you realize that if the rank of these matrices is P1 up to P, in each layer is PL, you sum up the ranks, you end up with a model that has just P indices, and the function f star will actually be quite complex given by the composition of all these layers together, but will just depend on this finite number of indices. It will be just a particular case of that function that then appears in the equations in a pretty like agnostic way of what it actually is. So all the kind of tools go through. So that's the sequence multi-index model. The second model that is, so what is the kind of so there are many caveats here, right? That I'm assuming some toy model for the data. But one caveat that we will remove in the next model is the fact that here I'm considering the keys and queries to be a very, very low rank matrices. So the rank must be finite while the embedding dimension goes to infinity. So in practice, this is not the case. The size of these matrices is usually, as I said, the embedding dimension over the number of heads. The number of heads in each layer is usually not very big, say 10. So the rank of the keys and queries is usually pretty high. So that's something that we can remove. And in order to do that, we introduce this attention index model. So again, it's a variant of the multi-index model. But now the index is not just a projection of the data in few directions, but it's a quadratic form. It's not a linear form, it's a quadratic form. So we have these W's, the teacher weights, that actually now have the index k that can be that is the kind of the rank, the size of that matrix that can be as large or larger even than the embedding dimension, just arbitrary. And then we have the index, the C, that's now the number of indices. So different layers, for instance, would be different indexes Cs. And if we take only one layer, we see here it's a little bit more kind of explicitly, it looks like the self-attention. There is the, again, with tight keys and queries, but that again is just a technical assumption that can be removed. And so again, the f star function, if we want, for instance, deep attention only teacher, it will be exactly the same f star function as for the sequence multi-index model. What is different here is actually how we solve this model. So if we just had a single index and there were no tokens, just t would be 1, this, and I will show you that in a moment, is actually a equivalent, at least from how we analyze it, to a quadratic, to one hidden layer neural network, feed-forward one, with quadratic activation. So that's what I say here. And the way we solve for the generalization error of that, okay, maybe question? So xmu, so I'm writing everything with all the indices explicit. So everything that is written are scalars. Okay.
Is this like having a value matrix that is rank 1?
So here, so if you want the value matrix in the attention index model, you need to mix the sequence index, the single index with the attention index. This really only accounts for the attention, for the key and queries, these W's. But you could, like, I mean, because all these things are kind of modular, you could say that the output is some other f tilde star function of these and the previous, all the previous terms. And the previous terms, they can account for the value matrix. But they multiply it not quadratically, just linearly. So you're right that in the way I wrote it here, the value matrices are not present. Okay. Yeah. Mm-hmm. Yeah, that's exactly, so that's everything that is it, the order doesn't matter, these are all scalars, and what is in the bracket is just a number for each of the indices. So this function takes that set, so it's a function of t squared times p parameters. Okay, because I mean, it's a choice. It's a bit ugly, right? But if I wrote it kind of more mathematically without the indices, then I find it even less clear what the dimensions actually are. So sorry for that kind of heavy notation. That is not very elegant. I agree with that. Yeah.
So how do you think like maybe something that goes to a linear function or a static function, or
No, F star is really arbitrary. It's really arbitrary. And it, if you want to model, for instance, 5-layer attention only network, then it's just composition of these things together. We kind of, the explicit form is a bit ugly, and one needs to kind of sit with it to see that indeed there is a explicit form of F star that puts together all the skip connections and the attentions and all that. Good, but it's just an arbitrary function, and it can account for interestingly, for instance, for the multi-layer attention only network. Okay, and now how it is studied. So as I said, it's related to the quadratic networks, and the quadratic networks are related to something that is called matrix sensing, and that's again a model where the tools go through and were developed. So we kind of go into that and pick from that to be able to write the explicit solution here. Okay, so now I have a few slides about how we solve these models. I will not say more about the sequence multi-index model because it really is, everything is the same as in the multi-index model. You just need to add the indices of the sequences. So that kind of makes some scalars vectors, but everything morally goes through. And in the attention index model, it's a little bit different. So we map the model into the matrix sensing problem. And then in that matrix sensing problem, that will actually, we use kind of the usual tools that I will not be detailing, the replica method, the approximate message passing, the bunch of random matrix theory. I will just tell you about the points that are different, interestingly different, and that make it work. So here I go away from sequences. I just go to the t=1 that will become exactly the quadratic neural network. So this is how the labels would be created in the quadratic neural network, and this is the model that would be learning. Here we have the nice property that if the width of the quadratic neural network is bigger than the dimension, then we actually know that the landscape is benign, that there are no spurious local minima, so the gradient descent a priori should behave nicely. And okay, so that maybe allows us to say something about gradient descent. That doesn't yet solve the problem. What allows us to solve the problem is to just take this expression and rewrite it. So this is just a trivial identity, nothing deep in there, and realize that we can write it as a trace of a product of two matrices. One of the matrices includes kind of the signal, and the signal is structured, and the other matrix includes the data. And then one thing that we realized, and it comes from previous papers, and to prove it using techniques from, again, previous papers, is a Gaussian universality property that is a bit surprising here, because it tells us here that this matrix, that is a rank 1 matrix, or not really rank, it's a rank 1 matrix plus identity, can be replaced. If we are just interested in the generalization error, we can replace this matrix by just Gaussian IID matrix. So of course, these two matrices do not look at all alike, but when it comes to the value of the generalization error, we can prove that it is asymptotically the same value for the two cases. So if that is the case, then this matrix Z here can be actually considered just IID Gaussian. And this becomes exactly a matrix sensing problem, so problem known in signal processing, with a signal S star that here has a structure. And this structure is just product of two matrices, and this structure we have to take into account. But when we realize what this structure is, when we actually consider the empirical risk minimization with the usual weight decay, so L2 norm on the weights, we realize that in terms, again, by one-line rewriting of things, that in terms of this matrix S, it becomes the nuclear norm regularization on this matrix S. And that's precisely the setting in which this matrix sensing is studied. And we have the approximate message passing algorithms and the appropriate denoisers, the kind of the key ingredients for the tools that we are using to write the solutions. So this is present in the literature. We just can put it together, and we end up here with an expression that at the end of the day is very simple for the generalization error of a student whose width is larger than dimension. If it is smaller, then it's either the same or slightly different when it is really small, but a bit more complicated. So this is the simplest one. So the test error is really just the number of samples over dimension squared, this constant alpha. Delta is the noise on the labels of the teacher. And this delta we have two equations that give us implicitly this delta, and epsilon is another parameter. These are two equations for delta and epsilon. The other parameters are known. This q star is just some second moment of the signal. The only function that is, the only one that I didn't explain what it is yet, lambda is the regularization, is this function here that is just free convolution of the spectral density of the signal times a Gaussian random matrix. So this is kind of where some random matrix theory kicks in. But at the end of the day, this is just a spectral density of a sum of two basic matrices. And this gives us an expression for the test error. So at the end of the day, the final expression is, elegantly simple. And we can start extracting things from it, for which I have maybe 10 minutes. So let me tell you briefly what kind of insights now we can get from these solutions. So the one I want to start with is from this paper, is about the lowering inductive bias and its consequences. So what do I mean here? So here I go to the attention index model, but I take a single layer and single head. So the data are created using a softmax, and here it's a centered softmax. I need to kind of have the mean that is 0 so that the large size limit works nicely. That's kind of a technical detail. So that's how that's the model for the data that I consider. Okay. Now, what I consider for the model that is learning, well, that's again a single layer of attention with the tight key and query. So these W's here are the tight key and query that have some size. Later, we will be considering again the R sufficiently big. And what the key property that is very curious here is again with the weight decay that, in the history of machine learning, sometimes you are putting the weight decay, sometimes not. It's quite curious to realize that these days, in the state-of-the-art models, there always is a bit of a weight decay. Maybe not a lot, but there always is. So you may wonder why, if in the history sometimes this was not needed. And here it maybe tells you why. Because if you put the weight decay for the same reasons as in the quadratic network, given the form of this function, this actually becomes a nuclear norm regularization on a matrix that is just the key and query multiplied. Okay, so just training with a bit of weight decay, nuclear norm, what it means, that you have a L1 norm on the singular values. So you actually enhance sparsity in the singular values. So you enhance very low rank of your keys and queries. And just the little weight decay here inductively gives you low rank of the keys and queries. And this is something, okay, that just at this level of information, it is known. It's something that is observed in practice. Here you see it very explicitly. And for us, if now we work through the equations, it actually allows us to link directly now the spectrum of the keys and queries, because now if the nuclear norm is crucial, it is interesting to look actually how the spectrum looks like, and write an expression for the spectrum in terms of the same order parameters as the expression for the test error, and see, in a sense, one-to-one, how here the spectral properties of the keys and queries that are trained, so at the end of the training, are related to the different terms that matter in the generalization error. So I didn't detail it here because it's a bit bulky in this model, but we have kind of this understanding for, very explicitly, that has been kind of speculated in the literature more empirically, but in this model we can write it very specifically. And moreover, what we observe numerically here is that the minimizer that the theory predicts actually is found by gradient descent. So these points here are runs of gradient descent at convergence, and they lie exactly on the line that we predict as the test error of the global minimizer. So it seems that also here, although we don't have an analog of the quadratic network proof here, this landscape is certainly not convex, but it seems benign in the sense that gradient descent actually goes to the global minimizer efficiently. Okay, let me skip through some of that. This one, here what I want to tell you is another consequence of this nuclear norm inductive bias. And that's, here again, I give you the softmax, as it is usually written and usually trained. The keys and queries are trained separately. But you may ask a very naive question, is why don't you multiply the keys and queries and train directly the elements of the product? Why do you train them separately? It should, over parameterization, maybe this will be a bit more parameters, but over parameterization shouldn't hurt. So a practitioner would tell you, oh, but this will be slower. Yeah, okay, maybe it will be slower. But if you ignore the speed, it should not be worse, right, in performance. That's what the kind of over parameterization popular kind of understanding tells us. Here, it's actually not the case, because if you trained the elements of the product, you would lose the low-rank inductive bias. And in this model, we can explicitly show what it would cost you in terms of performance. So here on the same data, we train, the purple one is we actually train directly the elements of the product's key and query. And the pink one, we train the key and query separately, as is done usually in practice. And this one actually has the inductive bias and works. The test error is low, and this one doesn't. And we can also draw it as a kind of a phase diagram as a function of the target width. And we see that what would not at all work if we were training the product actually works just a constant above the base optimal performance if we actually train separately the key and query. So this is a curious consequence that directly follows here that I didn't realize before, that you cannot train the product. That would really give you a worse inductive bias. We have one more, two more stories. I will maybe show you this one quickly about the scaling loss and power loss spectra in the attention. So here I write linear because so far, we worked it out for the quadratic neural network that actually ends up to be exactly have the same behavior as if we replace the softmax by a linear activation. We can also work it out for the softmax, but it's in progress. So what I want to tell you here is, I'm talking about these keys and queries matrices and that we are training them, and in my toy models, what they actually become. Okay, but you may ask, what are they in practice? Tell me what they are in practice. So there are papers that actually looked at this question separately from us. This is for fully connected neural networks, but this is a paper explicitly for the BERT architecture, for the llama architecture. And what is plotted here, the histogram, is the histogram of the singular values of the key and query matrices. So this is the query. Okay, this is the query, and this is the attention input, output. Okay, look at the query, and the key is similar. So you see that, while we were observing some kind of like bulk of noise and bulk of signal, here there are often kind of power loss in the kind of real architectures on real data. And is these power loss in the spectrum that quite possibly then translate to the values of the scaling loss of the test error as a function of the compute, the number of data and all that. So can we actually observe heavy tail outliers in the spectrum of the key and query in our theory? That's kind of a reasonable question once you see that. And the way to do that, you realize you have this signal S star that previously I was just taking as product of two matrices, Gaussian IID. Let me now take it such that its spectrum actually decays as a power law. So I impose that into the data that generates the labels. And if I impose that into the data that generates the labels, I go through the analysis I need some new elements here, notably non-asymptotic form of the analysis. That's something that a priori is not clear why it should be true. It's definitely not proven in the literature about these type of methods. But empirically, when we compare the prediction, the lines and the dots, the runs of the gradient descent, it just seems to be true also non-asymptotically when D and N actually are not infinity. So if we have access to that, then we can extract scaling laws from that. And we have this kind of phase diagram of how the test error actually goes down as a function of the regularization strength and as a function of the number of samples. And in a regime before the number of samples becomes so large that even the kind of rare small singular directions, you can learn them. So in these regimes, we actually see a Power law kicking in the test error that is related to the Power law in the spectrum of the decay of the spectrum of the S star. So this, in a sense, this phase diagram, correct me during the break if you think that is wrong, but is the first time you see a theoretical scaling law in a model that actually is not a linear model or a kernel or random features or NTK, etc. Here we are truly learning the features. The spectra that are jotted here are changing, truly changing, becoming non-trivial, and these are the power laws that are associated with them. So this is kind of a first step towards understanding more complex power laws. And when we draw the spectra of the resulting key and query matrices, they just look like the ones that you have seen in the empirics. And a last snippet, 2 minutes, okay, hopefully I don't need two minutes, is that one kind of deep question. It seems a very simple question again. I like these very simple questions that end up very deep, okay? Is why do you need the softmax? Do you need the softmax? So the empirical literature, especially the one on the state space models and MLP mixers and other kinds of architectures that do not include the softmax attention, actually suggest, oh, maybe you don't need the softmax at all or the attention at all. And then, so people were asking that. And then in order to come up with a task where the softmax is actually needed, this it's not even a paper, it's just a GitHub kind of post, but it's very, very, very well known now and broadly cited, is this needle in the haystack task. That is the one that if you ask a practitioner what is the toy task for which the softmax is really needed and the models without the softmax do not learn it, is this needle in the haystack. So you take a book of Shakespeare and you hide somewhere in the middle, Johan comes from Barcelona, and then your request is where Johan comes from. Okay, but then you must read through the Hamlet and you must find the one sentence that said actually Johan comes from Barcelona. And if you don't put the softmax in the architectures, this is very hard to solve. And with the softmax, it's actually working nicely. So this is well known in the literature that the softmax kind of makes the needle very visible in a way. Okay, but now when you look at the theoretical literature, and that's what I'm trying to do here, a lot of the theoretical papers about attention actually put the softmax away. That's complicated, so let's put it away and try to understand the training without the softmax. So okay, it's a valid, way to make a more mathematical tractable version of it. But if your methodology cannot deal with the softmax, you hardly can show then why the softmax would be needed. Okay, so that's one thing. So can we actually have a theoretical justification of how the softmax is needed? So can we have a version of this needle in the haystack that is analyzable with our methods and where we can show, look, if you don't have the softmax, it doesn't work. If you have it, it works. And this is this single location regression problem that is, in a sense, you can think about it as a toy needle in the haystack on toy data that is analyzable. And it's almost a linear regression. You see that I'm generating here the labels by just making scalar product with one vector, V star, of one of the tokens. So in my T tokens, I choose one, and I make a scalar product with some ground truth vector V star, and that's the label. And then I present you the whole sequence of tokens and the labels, and I ask you, learn the function, learn to pick which was the right token that you should multiply with that vector, and which was the vector, both that you need to find. And now there needs to be some structure in how you actually chose that which token it was, otherwise it's not doable. There are two versions of that. Either you choose the token that had the biggest scalar product with another particular vector k star, or softmax, biggest scalar product with it, or you choose a random token, but then you add a little bit of a signal in it. You add a spike to this matrix in the direction of k star. So that are two versions of how actually to turn regression on sequences of tokens into a needle in the haystack. And on this model, okay, then the way we learn it, we actually, so here we learn it with something where the query is not present. It's not a self-attention, it's just attention. We are attending to one of the vectors. We are not comparing to the others. So that's how the teacher looks like. And here I have the value. So actually the value will be this V star matrix, and the K star from the model, that the key will be learning that K star. And this is a version of the sequence multi-index model. I can solve it again with the same with kind of the same toolbox. I just need to add the token indices here, and I can show here for both the versions of the model and as a function of the sequence length that the softmax type of activation actually reaches the Bayes risk. This is in population risk. We also have the plots for the empirical risk, while the other activations such as linear or other 1 plus ERF or normalized soft plaques or some kernelized attentions actually would not reach the Bayes risk. And this is becoming worse and worse as the length increases, which kind of makes sense because as the length is larger, all the other tokens add you more noise unless you are able to pin the right one. And the softmax is able to pin the right one for you. So that's kind of a toy in the needle in the haystack that is fully analyzable. And I'm already way over time, and I will stop here with just the partial list of all the other things that in principle can be incorporated into the sequence multi-index model or the attention index models that are, now a playground with a methodology that, partially is rigorous, partially is not. This, as it has been for the multi-index model, those that are not, it will be in the community over time. That's how it works. But it's a very rich playground to actually now study the different ingredients and different properties of what you see in the actual training with attention with toy transformers. So this just gives us a lot of possibilities to work on in the next few years. And I will end up with thanking you for your now you know what, and some nice picture of our